Osmi, do you want to start?
Say again? Let's start. Yes. So welcome everybody to today's seminar, Modeling Antarctic Ice Adaptive Mesh Refinement. You will learn about recent progress and the challenges in the modeling of the response of the ice sheet to climate forcing using adaptive mesh refinement, AMR for short. In a very simple words, AMR tries to find a balance between coarse and fine discretizations of a physical problem in an automatic way, while achieving good accuracy and computational savings. The seminar will be presented by Dan Martin, who is a computational scientist and group leader for the Applied Numerical Algorithms group here at the lab. The interesting thing is that his office is 15 yards perhaps from my office. He's in the 593101 while I stayed in my office today. So Dan got a PhD in mechanical engineering from UC Berkeley and joined LBL as a postdoc in 1998. His research involves the development of algorithms and software for solving systems of PDEs using AMR, finite volume schemes, and also he works on the development of support for the Chombo package. With that, Dan, please.
All right, thanks, Ozzy. So this is the first talk I give to actual people in 2.5 years, so we're a little rusty, but it's already so much better than staring at my screen and talking to the air. So hi. So first of all, a little bit about who I am. I grew up outside Philadelphia, and then I went to high school in Orlando, Florida. I did my undergrad in mechanical engineering at the University of Florida. Then, as Ozzy said, I got my PhD here, just down the hill. Then I came up the hill to the lab as a postdoc 22 years ago and never actually left. And then you turn around and you're like, well, I've been here 22 years. Currently, I'm the group lead for the Applied Numerical Algorithms group. My focus, like Ozzy said, is on developing algorithm software for solving systems. Let me get this out of the way. Of partial differential equations efficiently and accurately for real applications that show up in DOE applications. Off work, I'm married. We have 2 boys, 15 and 12. And I used to have, before the pandemic, I had hobbies like cycling, music, and travel. Now I just sit in my living room. So this story begins back in 2002. And this is the satellite picture of the Larsen B ice shelf. So in some of these ice sheets, basically what happens is the ice flows off the land and flows into the sea. And when it begins to float, it goes from being an ice sheet to an ice shelf. So an ice shelf is floating ice that's connected, that's being pushed out from the land over the sea. And think of it as a shelf because you can think it's just like a shelf. You have ocean underneath it. This particular ice shelf is on the Antarctic Peninsula. So this is Antarctica. This is the Antarctic Peninsula, and it's right around here. And the satellite passed over in January, on the end of January. You can see that this ice shelf, so this is the ice is flowing from left to right. This is the ice shelf. The black is the open sea. And you can see that there's always melt ponds on this ice shelf, which turned out was important because over the next couple of weeks, the ice shelf disintegrated. So, over about a month, the whole thing disintegrated. And this took me by surprise because people thought up at that time thought that these ice sheets were pretty stable. Like they could, they changed, but they changed on sort of, glacial timescales. But what really surprised what happened afterwards, because so, like I said, about, 1,250 square miles of ice shelf just disintegrated in about a month, likely due to the exceptionally warm summer. There's melt pools in the ice. You have this thing that happens that, what happens is these melt pools form. And the theory is that because they're darker than the surrounding ice, they tend to heat up and they tend to sort of act like daggers in the ice. And basically, you can think warm water in an ice shelf will act like it will basically cut its way through and you just shatter the thing. And what really surprised everyone was that the glaciers that fed them, the ones on the land, sped up. And they sped up by about 300% on average. And the mass loss went from 2 to 4 gigatons per year to about 22 to 40, between 22 and 40 gigatons per year in 2006. So that's a massive change. And it was an indication that these things are maybe much more dynamic than people expected and people understood, had thought they were. And so why do we care about this? Right now, there are two ice sheets on the planet. One is the Greenland ice sheet, which if it were all to melt, sea levels would go up by about 5 to 7 meters. And the Antarctic ice sheet, which contains a whole lot of water. If the whole thing was to melt, it would be 57 meters of sea level rise. Now that's not likely to happen, but there are, for various reasons, this region here, which I'll go into more in a bit, so we have East Antarctica and West Antarctica. If this were to go, we think there's about 4 to 5 meters of sea level rise potential in the vulnerable parts. So this matters a lot if we live on the coast, right? So a lot of that is below 4 to 5 meters of sea level from sea level. And as you probably know, sea levels are rising. And this is a little bit old of a slide, but at the time, about a third of the sea level rise was coming from the ocean thermal expansion. The fact that as you heat ocean, it warms up. I mean, as it warms up and expands. About a third was coming from the small glaciers, ice caps, and about a third was coming from the ice sheets. And this, like I said, is an old plot, but you can tell that the contributions from the ice sheets is obviously increasing, and it's also accelerating, right? These curves are trending down. So this matters. And the state of the art back in 2007, which is about when we got started on this thing, the IPCC's AR4 report actually called out the existing ice sheet modeling capability as being inadequate. They couldn't resolve that. They couldn't actually model what they observed, when they break up the Larsen ice shelf. So DOE said we spent a lot of time building building numerical models to solve these kinds of problems, so we can help. And so the DOE OSCAR is the Office of Applied Scientific Computing Research. So they're the ones who do like computer modeling and applied math types of things. They put out a call for next generation ice sheet model development. And the result was the BISICLES project, which is 6 small funded projects, about 1 or 2 people each. And one of those projects was the Berkeley-led effort, which was called Berkeley Icicles, which were bicycles. And it turned out that we had some synergy with people in the UK also funded someone to a postdoc to do exactly the same thing at the same time, so we joined forces. And so Bicycles is this multi-lab, multinational effort. And basically me and one other guy, but anyway, so how do ice sheets work? The way ice sheets work is that imagine that the snow falls and it doesn't melt, right? It's cold enough where it doesn't melt. And so next year snow falls on top of that and it just piles up over hundreds or thousands of years. And at some point you have so much ice, so much snow that the snow on the bottom of it gets compressed into ice. And this continues and continues and continues. And at some point it becomes so thick and so heavy that it actually begins to spread under its own weight. So you think of it like, if you pour like a big pile of honey on a table, you'll watch it sort of, the pile will sort of spread in a viscous way out, right? Or you can think of pressing a toothpaste tube and the toothpaste pushes out under its own weight, under the pressure. So you have this tendency of ice to basically fall here and then flow, like I said, squeeze its way out toward the oceans. And one or two things can happen. It can terminate on the land, or a more interesting way, it can like it did in the what we just saw. It can flow out over the ocean, and the point at which it begins to float is known as the grounding line. And the part out here is the floating part is called an ice shelf. The grounded part is an ice sheet. And this whole thing, when an ice sheet flows over out into the sea, is known as a marine ice sheet. And it turns out what we saw in the Larsen ice shelf was the effect of buttressing. So it turns out these ice shelves buttress the upstream flow. They push back on the upstream flow and hold it back. So when you weaken or lose these ice shelves, suddenly you unblock that, and this conveyor belt of ice sort of accelerates. And then as the ice accelerates, you imagine it would thin because you have a finite number of ice. So the ice sheet accelerates and thins. And as it thins, that means the grounding line will retreat, because at some point the point where it floats will start to retreat. And so it turns out there's a theory that says that if an ice sheet is sitting on, and the grounding line is sitting on a bed that gets deeper as you go inland, that's an unstable configuration. So it's a marine ice sheet instability, and it will continue to retreat unstably until it finds a stable position. So it turns out if we kick these things, and they can go, you can wind up with instability that just basically goes on forever or for a long time. Another reason why I really care about this is this is the a plot of the actual bedrock under Antarctica, right? When you move the ice is what you would see. And the key here is that all this blue area in West Antarctica is under sea level. So a lot of this ice is sitting on bedrock that's under sea level. And if you look at cross-section through a very carefully chosen cross-section, you can see that it's actually pretty dramatic. This cross-section actually goes like basically along this way. So, and you can see two things. A lot of it's under the sea level. And also you can see that they have this big unstable configuration where it, like I said, if the bedrock gets deeper as you go inland, it's an unstable configuration. There's a lot of things which can sort of get in the way of that, but you know, that's a cartoon basically. So we want to make an ice sheet model. So what does it look like? This is basically the process that happened. Like I said, snow falls on the ice. It basically accumulates. At some point, the ice flows out to the margins. It may flow out over the ocean. If it flows into the ocean, then you have ocean circulation underneath, which can deliver heat to the underside of the ice sheet and melt it. And that's sort of the thing. So if you have an ice sheet model, sorry, my screen is blocked. This is the equation that governs that describes the evolution of the thickness. So if H is the ice thickness, the HDT is equal to these terms. So B is the surface mass balance, so the amount of snowfall on the ice, or maybe the melting if it's lower. M is the subshelf melting, so the melting from the underside of the ice. And then this term is the flux divergence. So imagine if I'm standing here in a particular part of the ice and ice is flowing from upstream and flowing downstream. If more ice is flowing from upstream than is leaving where I'm standing downstream, then the ice will rise, right? The ice will thicken. If where I'm standing, if more ice is leaving where I'm standing than is arriving, then the ice is going to thin because the ice is leaving the point where I am. So that's what this term expresses. Basically the flow of ice in and out of where I am. This is actually the dynamics of this is the actual ice sheet model that we built. The rest of it is just source terms we get from climate model, other climate models externally. Ice itself is a non-Newtonian viscous fluid. It's shear thinning in the sense that it turns out that as you shear ice, the viscosity goes down, and that affects the dynamics in some pretty interesting ways. It tends to create these shear margins where the shear tends to be concentrated in these very narrow margins, for example. Because it's we really know this Reynolds number, it's well described by the Stokes system, if you're familiar with that. And people try to solve those equations, but they turn out that they're really hard to solve. They're very expensive. They're computationally expensive if you're trying to solve on a computer, and they're hard. They can be intractable sometimes. So people try to approximate them in some way, doing some sort of approximate Stokes method. And the way people generally go about this is they use scaling arguments to produce a simpler set of equations. So one common way to think about this is that you can expand your equations in the ratio of the horizontal to vertical to horizontal length scales. So because ice is like kilometers thick, so it's thick, but it's also hundreds of kilometers wide. And so it's dynamically very thin, and you can treat it as a very thin membrane if you're careful about how you do it. And these approximations lead you to a simpler set of equations that maybe is easier to solve. You wind up reducing dimensionality of things. It's often like, for example, the most common way to do it is to expand these in this ratio epsilon, and throw out the terms that are order epsilon squared or greater, and so you retain the terms that are linear in epsilon. And that system is known as the first order equations, or the Blatter-Patten system. And that's still three-dimensional, but it's you pull out one set of equations. So instead of having three coupled nonlinear elliptic equations, you have two. And they tend to be a little bit easier to deal with. An even simpler set of equations says, well, this thing, so then why don't I just depth them integrate and treat it as a 2D system? And the simplest way to do it is they're basically order epsilon, order one, basically. You throw out all the terms that have epsilon in them. And they tend to be easier to deal with, but they tend to be less accurate. They tend to be accurate only in specific circumstances. The model we use is actually a clever model that was put together by Christian Schoof and Richard Hindmarsh, where they use the asymptotic structure of the full Stokes system in a much more clever way. They actually expanded two different parameters, the epsilon I just mentioned, and also the ratio of shear versus normal stresses. And it turns out if you do all the math that, and you can wind up with a system that you can actually vertically integrate, so you solve a 2D system instead of a 3D system, but you can actually reconstruct a full 3D system, or 3D field, and it winds up being as accurate as the fully 3D system. So it's a nice. The point of this is that it's important to think about your system and think about what you know about your system before you just jump in and try to solve things, because you can often try and find ways to make it simpler and more tractable by just using a little math. So math comes in all these different places, and this is one of the places where it's important because it makes the whole system. It means you can spend your time worrying about solving for things that are important instead of things that aren't. And then the next question is, how do we actually solve these on a computer? For people who are familiar with this, computers are really good at doing simple arithmetic, like addition, subtraction, multiplication, and division. When I talk to elementary school kids, I basically tell them, you're as smart as a computer. You can do everything a computer can do, only you a little bit slower. You can't do it, a million times a second. And unfortunately, the equations of physics are usually continuous and complicated. For example, this, the red equation is a heat equation. I think most people have probably seen this by now, but the way we approach this is we break the world into small pieces. So if we start with this continuous green domain, we break the world into small pieces, which we'll call cells, by laying down a computational mesh in the domain. So basically just laying down a mesh and dividing the world into little bits. And then we can approximate our continuous calculus equations on this by using a set of simpler arithmetic equations on these small bits. And one characteristic of these meshes is the cell spacing, or we'll call dx, because it's a change in x as you go across the thing. And to give an example like this is a relatively coarse mesh. This is a much finer mesh. And so one example is if you're approximating derivatives, you can approximate df dx as the difference in f divided by the difference in x, right? And you can do that in different ways. You can do it as center difference, a right-hand difference, left-hand difference. There's different ways of doing it depending on what you're doing. But this leads us to what we're doing here, which is, like we said, adaptive mesh refinement. You can imagine that the finer mesh, the more accurate your solution is going to be. The more pixels in digital camera, right? The more resolution you have, the more accurate your solution is going to be. But the finer the mesh, the more unknowns you have to solve for it. So, and the more unknowns you have, the more expensive it is to solve. For example, in a 3D world, if you're solving like 3D gas dynamics, just taking dx by a cutting dx by a factor of 2 means the cost of your computation goes up by 16, by a factor of 16, because it turns out you 3 dimensions, 2 to the third, and then you actually have to take a shorter time step as well because of the smaller cells. But that means that getting fine resolution can be horrendously expensive if you do it everywhere. But it's also true that in a lot of places you need fine mesh only in this high resolution only in some places, but not others. So adaptive mesh refinement is a way of locally refining, putting fine mesh and the computational cost that's associated with it only in certain regions. So the idea then is to improve the accuracy only where you need it and use coarser resolution and not spend the effort solving where you don't care about it. The way we actually do this is we do what's known as block structured refinement. So imagine if you start off with a uniform coarse mesh, which is the black one, and then you refine largely rectangular patches in that domain. So this blue region, these blue blocks are a factor of 2 finer than the black mesh. This red mesh is a factor of 2 finer than the red mesh, and you keep nesting the meshes inside and go as refined as you need. The only thing is these are adaptive in the sense that you can add these and subtract them and as the solution evolves. So if you have a shock wave moving through the system, you can add and remove computational mesh to follow that feature, or as things evolve, as things emerge. You don't need to know in advance where it's going to be because the dynamic parts of this can pick up what you're looking for and lay down mesh there. So the idea is that AMR lets you dynamically focus all your computational effort, which is limited, right? Even on the supercomputer, you're still limited by how much you can do. And it lets you focus it where you need it, which it turns out for ice sheets, that's really important because you need really fine resolution, like only in particular reasons, especially around the grounding line. It turns out we need really fine resolution. So the bicycles code we developed is a scalable adaptive mesh refinement ice sheet model. So the idea is we use AMR and to do an ice sheet model. Everything here I think I've already talked about actually. And it's useful because, like I said, in ice sheets, if you look at this is the plot of the velocity field of Antarctica, right? You see a lot of very fine regions where things are going on, but there's a lot of regions where not much is going on at all. In West Antarctica, for example. And it turns out you need really fine resolution to resolve things at the grounding line, but less so other places. So So which means this is it's the poster child for adaptive mesh refinement. And we have two types of target problems. One is basically we do spend a lot of time looking at sort of this idealized ice ocean interaction test problems, trying to understand how the dynamics work, like how ice sheets work in these sort of idealized test cases to understand, basically we're still trying to figure a lot of this stuff out. And also it's a way of sort of comparing different models across the community and make sure and to understand who's doing well, who's doing badly, and why. But then what we really care about is doing realistic full scale, fully resolved, full continent Antarctica, right? That's what we care about, because that's what, that's gonna let us know what sea levels will be like in 20 years. So we want to basically do Antarctica. We want to basically resolve down to say 500-meter resolution, which is, pretty fine. And it turns out that if you do that with adaptive mesh refinement, you want to have meshes look like the one on the right. So you can see it's pretty finely resolved around just the margins. So like places where we have ice streams, or places where you around the grounding lines. Basic visualizations, we have our baseline models are logically rectangular mesh, like I said. We have a map coordinate in the vertical direction as the ice gets thinner and thicker. We have a two-dimensional equation for ice thickness, as you can think of thickness as evolving in the way I just described before. And then we solve this vertically integrated momentum balance, which gives us this 2D nonlinear viscous tensor solve. So this is we spend about 90% of our time solving this equation down here. It's an elliptic equation, which is nonlinear, and it's just, annoying. But we've gotten very good at solving it over the past 10 years. And then we evolve energy using an enthalpy formulation. Because there are a bunch of different, you can imagine there's a lot of things you have to do very specifically for doing adaptive mesh refinement, and you do them over and over again. So if you're doing a gas dynamics application, or you're doing ice sheets, or you're doing, fusion, they all need the same pieces, algorithmic pieces. And so we rely on these software frameworks to sort of encapsulate these things and be able to build reusable software. So it made it a lot easier to build an ice sheet model because we had already done it for other things. And so Chambo is our sort of our place where all this software framework lives. It's been developed for the Berkeley lab. It's highly scalable. It's been developed for everything from laptops to supercomputers. And it's just a way these are just pictures of different applications that we've done using Chambo, everything from atmospheres to flow through fractured rock. This is a sea ice formation model we made, more fractured rock, ice sheets. This is a fancy geometry, and this is a cross section of the tokamak. All these things are things we can do because we have this sort of software framework to build upon. So now we have an ice sheet model. What am I going to do with it? First thing has been coupled with various other models, right? So one of the first things we did was we coupled our ice sheet model to an ocean model. So we took there's an ocean circulation model called POP. We made a version of it called POP2X, and we coupled it to bicycles. And obviously POP plus bicycles becomes popsicles. We didn't pick the model for that reason, but it worked out. And so one example of that, and the idea is that you then have an interactive coupling between the ice and ocean. You can see how the ice circulation under the ice shelf can affect the behavior of these things. So we have this one test problem we ran. We ran a lot of test problems. The one sort of industry community standard test problem is you have this ice shelf, this basic ice stream in a trough, and it's flowing this way. And you have an ocean cavity here. And what you do is you perturb it by heating the outer the far field ocean by up to 1 degree Celsius. And you let that go for 100 years. And after 100 years, you make it cold again and drop it down to negative 1.9 Celsius. So you have a swing of about 3 degrees Celsius, which doesn't sound like much, but if when you have warm water under an ice sheet, it hits like a blowtorch. So this is the flow here is going from left to right. This is showing the ice surface, and the color you're going to see is the melting, the actual melt rate. So this is just showing a movie of what happens. So you can see the warm water got down there. So you can see that all this melting started to happen around here. And you can see also the grounding line is now starting to retreat. The ice shelf is thinning. You have this fairly complicated flow pattern leading to some fairly complicated geometry, right? Because you also have Coriolis forces, which tend to make things flow to one side, and which is why this tends to be lopsided to one side. But at some point, it decouples from the sides and went up with this gigantic ice tongue, which then starts to fragment. And basically, that's pretty untenable. So at some point, it just breaks off like that. And then you have this little stub of a tongue, and even at some point, even that goes away. And we're about 65 years in. And you can see that there's a lot of melting going on. There's a lot of flow because you have melting, warm water getting in and melting, and then you have this pump going on, which generates from the convection of right around the grounding line. So a lot of flows that are going, in this sort of pattern along here, and you have this plume, melt plume flowing out. And that's when I let it run out to 100 years. So it was this is a pretty exciting model to run, because obviously a lot happens, and a lot of very annoying things had to happen in this to get these pieces of software to talk to each other and in the right ways. I mean, it's amazing how many sort of weird things you have happen when you do these things. So after 100 years, you can see that we cooled down the far field temperature. It took a couple years for the cold water again, but now it basically turned off the melting, and you can see the ice shelf is starting to regrow. Basically, it's being pushed out, and you can see the grounding line is very slowly re-advancing. It turns out it doesn't. One thing about ice sheets we've learned is it's much easier to blow them up and destroy them than it is to regrow them. So the regrowing after 100 years, you're not fully restored, and that's an important lesson for these things. Is that in a lot of cases, these things are reversible, or they are just much harder to rebuild once you've lost them. I'm not going to. This just goes very slowly and it's very boring the rest of the way. So. Another type of coupling we've done is looking at the solid Earth response. So we've coupled to, you think an ice sheet's sitting on the ground, right, bedrock. It's pushing down the ground because the weight of the ice pushes down the ground. And as you load or unload that, as the ice sheet thins or thickens, the ground responds and goes up and down, right? So if you unload it, the Earth will respond and bounce back up again. This is known as glacial isostatic adjustment. And like I said, what we're thinking about right now is the fact that this unloading can lead to a rebound. And it turns out that one theory is that this rebound can potentially help stabilize the ice sheet, because you can think about, so you have this flow from left to right, right? Here's the grounding line, here's the bedrock. As the ice sheet retreats, you reduce the weight, and in theory, the rising bedrock could help stabilize it by reducing that negative slope and sort of pushing it up out of the water. How that happens actually depends on the mantle properties, so how soft the mantle is and how fast it rebounds. And also the rate of how fast your ice sheet is changing. If it's happening too slow or too fast, it changes how where the response happens. And so recently we coupled bicycles to a solid Earth model to see what would happen. And this, especially because there's some evidence under the West End that the mantle under the West Antarctic ice sheet is hotter and weaker than elsewhere, which means it's going to be much more responsive. And so the result we found was that actually, I think I have a better slide for this. So this is the Pine Island Glacier, which is one of the glaciers in the Amazon Sea. It's one of the more responsive ones. Those are the ones that are changing very quickly. This is change in thickness above flotation. From thickness above flotation is a quantity we use to describe the potential for sea level rise. So if ice is, for example, like if ice is floating in the water and it melts, there's no potential for sea level rise because it's already floating, right? It's like if an ice cube in a glass of water melts, it doesn't affect the level of the water. But if the ice is sitting partially submerged, then it melts, then it will be some contribution to sea level, but not a lot, but not as much as if it was sitting directly all the way above. So thickness above flotation is the amount of ice above the actual flotation point, and that's what matters for sea level rise. So if all the ice is sitting at the flotation point and it melts, then nothing will happen in terms of sea level rise. So that's what we actually care about when we talk about response of Antarctica and stuff like that to climate forcing, is when you think about sea level rise. So this is the look at this is for one example with the regular forcing, without the glacial isostatic adjustment and without GIA and with GIA. After 150 years, you can see that you have a lot more ice loss and sea level rise without including this GIA feedback. And that's because the bedrock is rebounded. And so this red, it shows just the right around the grounding line and right around where things are active, the unloading and thinning of the ice actually caused enough rebound that it actually has impact. This is a plot of sea level rise versus time for without the GI adjustment and with the GI adjustment. You can see that it's a difference about 17 meters of sea level rise for this one little glacier, if you take into account. And this is another the different just a bunch of different scenarios. The other thing that it turns out that is important about this is the rate at which it's retreating. So let me go back to this other figure. If the retreat happens too fast, then it turns out that by the time the bedrock responds, the grounding line has already backed away, and so it's too late to actually have an impact, because raising the sea level bed doesn't have an impact on the actual ice sheet. So what matters is the fact that is a case where the ice sheet is retreating at about the same time scales as the GIA adjustment. So it has to be slow enough where it actually can impact it. And that's one of the things we found in this paper is that's what matters the most, whether you have an impact or not, is the actual rate of retreat and making sure and whether it's on the same time scales as the adjustment. We also have another thing is that there's actually water under the ice. And if you have melted water under the ice, it can lubricate the bed of the ice and change the basal friction. So it can speed up or slow down depending on how much water is. And this is particularly true in Greenland, where you have, I don't know if you've seen pictures of these massive melt ponds and melting on the surface tends to flow into these gigantic lakes, which at some point then, water on top of ice is not really a tenable place. And so at some point, usually they form these channels called moulins, which then drain the water to the bed. And these lakes drain, instantly almost to the bed. So you flood the bed of the ice with water, and you can actually see that the ice accelerates because you've suddenly lubricated the bed. And you can see, if you look at people have GPS stations on Greenland, you can see the ice accelerating, decelerating as these flood events happen, as you get water to the bed in various places. But then as things evolve, these things tend to go from a very distributed pool of water, right, to which then has a strong effect on friction. At some point, they tend to form these very efficient melt channels, and then which then manage to transport the water from up here out to the sea. When that happens, it becomes more efficient, and then the ice slows down again because you remove that lubricating effect. So we want to be able to model this and understand how this subglacial system impacts it. In Antarctica, you tend to have systems of subglacial lakes which fill and drain in sort of a similar way. So we're going to be able to model this, and you can imagine the same sort of thing, right? You have this transition between these large, pools of water or sheets of water and these sort of spontaneously forming channels. And so we built a subglacial hydrology model, which is also adapted to mesh ceramics. It's also a nice candidate for it because you don't know where the channels are going to be, you don't know when they're going to form. And so this model adapts to mesh as channels as well. So this is an example of a test case where we have these channels forming, and you see the mesh is refining around the channels as they evolve. The status is we're still testing it, we're still writing the paper. And the next thing is to couple the bicycles and actually be able to model the coupled subglacial hydrology system with the ice and actually model this changing of the basal friction and the ice speeding up and slowing down as it goes. So it's a pretty exciting thing. This is actually fairly new. We're still, like I said, we haven't actually published anything on this yet. We're also coupling to the larger Earth system models. We're coupling both to the DOE has its own global Earth system model known as E3SM, and we're currently coupling to that. The idea that you have the ice sheet sitting in this climate system, and then the model says, well, you have this much snowfall, and then the ice sheet responds to that, or this melting, this much snowfall, and then adapts and then responds, and then if it melts, then the sea levels go up, or it's the idea is how does the thing function in this coupled climate system. Bicycles has also been coupled to the UK Earth system model known as UKASM, and they're slightly ahead of us. So they actually have the first fully coupled Antarctic response paper. So that came out last year, which was pretty exciting. The end story of this is actually coupling is hard because it turns out driving a single model is easy. Once you start coupling models, you have to step back and you put your hands up, and then you let it go and hope it goes someplace sane. So these things are really hard. It's the only thing I have to really say about that. Another thing we can do is now we have this model, we have this AMR model. We can look at what exactly the resolution requirements are for doing Antarctica. So we came up with this test problem. We started with the full continent of Antarctica, basically initialized to the present day. And we can run, like I said, we can run AMR and we can basically choose the resolution we're going to resolve at by just saying how many levels we're going to add. And so the experiment we ran was we did a set of 1,000-year Antarctic simulations. And at the initial time, we did it for a series of different resolutions from 8-kilometer resolution down to 500-meter resolution. And basically what happens, we subjected all the ice shelves to this really super extreme melting, basically like 500 meters per year. So super thinning, just hit them with a sledgehammer and see what happens. Because remember as you clobber the ice shelves, the floating parts, that then unblocks the ice sheets, and then you have this dynamic response that we're all worried about. And then, so we did this for a series of resolutions from 8 kilometers down to 500-meter resolution, finest resolution. And we evolved them for 1,000 years. And this is what happens as an example, just to show how it reacts. So you can see that once you clobber these things, they retreat very quickly. Unfortunately, this is much smoother on this than it is on that, because this is going through Zoom. I will also say that this movie is actually playing right now on the screen out there. So if you want to look at it in a better way later, that's kind of, I didn't time it that way, but that came out well. So the point is that you have this massive retreat, right? When you start clobbering ice shelves, and you can see that you have all of West Antarctica over here has been clobbered. All the ice is gone. And just to show you how the adaptive mesh refinement works, this shows what the mesh refinement is. So black is the finest resolution, and this is the coarse resolution. So you can see two things, that it's mostly around the grounding lines, and you can see that you can watch it dynamically adapt as the mesh, as the ground lines retreat. So if we had to resolve this entire region at this final resolution, it'd be horrendously expensive. But because we're only resolving where the action's happening, it's a lot cheaper. And it's actually possible to do this. So the results we got, the upper plot here is a plot of the contribution to sea level rise. So the black line is 8 kilometers, and then 4 kilometers, 2 kilometers, 1 kilometer, 500-meter resolution. And so first thing you can see is that 8-meter resolution doesn't do much. It's actually, it doesn't have a lot of response. But then as you add resolution, you get more and more response, more and more contribution to sea level rise. And I would say that if I was going to make predictions, I would want to use one of these two lines up here that are pretty converged. So you can see that these are actually what you need to get what I would say is the right answer. Because then you can also see these are starting to converge to something that as you change it, you're not changing the solution much. And if you look at what's happening, the bottom plot here is a rate of change. So this big spike is the collapse of West Antarctica. And you can see that it happens at different times depending on what your resolution is. And like I said, at the coarse resolution, the black line, it doesn't ever collapse. So what's happening? This is the plot looking down on a plot of oops, that wasn't supposed to happen yet. Looking down on West Antarctica. So this is the Amundsen Sea. This is the Weddell Sea and the Ronnie Filson ice sheet, ice shelf. And so what you're going to see is what happens. The green line is the grounding line. And so this is Thwaites Glacier, which is one of the big ones. This is Pine Island Glacier, which we looked at earlier. So we're going to see is that if we're fully resolved, basically you can see this grounding line retreat, and basically ice will drain out through the Thwaites Glacier into the Amundsen Sea. So this is what happens if you're actually fully resolved. And you can see that it collapses and you basically go in and everything flows out through the Amundsen Sea. If you're under resolved, it's the same thing with 4-kilometer resolution. This one stalls. And so instead of flowing out here and collapse this way, you basically come in through the Rutherford ice stream, and everything drains out through through a different mechanism. So if you're under resolved, you get the mechanism wrong, you get the timing wrong, you get everything wrong, right? So this is an example of you need to be resolved. You need to have the right resolution to be able to resolve the physics that you need, or else you're wasting your time. And this was we've been trying to make this compelling case to people in the field, and they're starting to. It was pretty before in mid 2000s when we first started. People didn't take resolution very seriously. It was like, well, this is what I can afford, so this is what I'm showing, and showing people that you're getting wrong answers and you're getting answers that are meaningless was hugely effective. To the point where we have paper we submitted, and people were like, where's your proof that your resolution is correct? And it was both annoying and yeah, we made a point at the same time. So the point is that, you know, if you're sufficiently collapsed, if you're sufficiently resolved, you get this complete West Antarctica collapse. But lower resolutions produce lower response. And it looks like you need, the point is you need a resolution of 1 kilometer or better to get the right answer. And that's kind of important. And the other point is that under-resolved resolution give you the qualitatively wrong response as well as the quantitatively wrong. You're getting everything wrong. Something else we can do now we have this model is look at, so we've just hit all of Antarctica with this sledgehammer, right? What happens if we look at pieces and see what happens then? So we can look at where is Antarctica vulnerable. So the next step was to take that sort of massive sledgehammer forcing and restrict it regionally. So what we did is we break Antarctica into 14 sectors. Each represents roughly a drainage of each basin. So, you know, ice in this blue region flows out to the Amundsen Sea, ice in this green region flows out that way, etc. And for each sector in turn, we applied this forcing just to that sector, and then ran for 1,000 years to see what happened. And this was published back in 2019. We even got the cover, which was neat. So the answer we got is that this is the plot of Antarctica with the different sectors I just showed, and the size of the circle tells you how much sea level rise you get if you just clobber that particular ice shelf, all the floating ice in that sector. And so you can see that you have 4 sectors that are massively vulnerable, and they're all connected in some way to this vulnerable section of East Antarctica. There are some sectors which are sort of moderately vulnerable, which produce, you know, between 0.5 and 1 meter of sea level rise. And then there's a bunch of sectors which aren't really all that vulnerable at all. That basically you clobber the ice shelves, nothing much happens. Just to give an example to show you what happens, I'll show another movie. This is just clobbering this sector, which it turns out is, you think of it as East Antarctica, but it has a little pathway into West Antarctica, and that's what matters for this one. So you can see we're melting the ice here, and it's because it can get into this vulnerable plot, even that little bit is enough to make the whole thing collapse. And so you see, basically, it runs through and eventually clobbers this whole West Antarctic sector. Just because you melted the ice shelf over here, and because it had a pathway into the vulnerable areas, and it just keeps on going, keeps on going, keeps on going. So it's a measure of just how vulnerable this part of West Antarctica is. So you can clobber if you get it from any of these different directions. It will basically collapse, and that's 4 meters of sea level rise. The other thing we can do as we develop this model is we're always adding new physics. So one of the things we were adding is the concept of damage. So all our models are based on sort of idealized. So think of ice with no fractures, no, just like, you know, just beautiful, clean, pristine ice. And that's how we base our flow parameters on. But it turns out real ice is damaged, right? Real ice has fractures and crevasses. And the question is, how does that affect the ice sheet? So here's a movie showing basically Pine Island Glacier again. And the point is, you can see that first you can see this rifting and fracturing, right? So you these calving events happening up here as the damage propagates and the cracks propagate and form. The other thing you can see is if you zoom in here, you can see this shear margin area has a lot of crevasse, all this texture, lots of crevassing, lots of broken ice, lots of not ideal stuff going on. So it's pretty exciting, and this is absolutely not in our model. It's sort of our model. We can sort of fake it, but it's not being handled in a dynamic way. So the question is how. And I love looking at this movie because it's really cool. So we make another variable called damage, and it represents the extent to which crevasses fully penetrate the ice. So where this parameter is 0, it represents undamaged, pristine ice. Where it's 1, it represents fully damaged ice, to the point where it has no structural integrity, and the crevasses have penetrated it. And you can evolve this damage. So you can think of it, if you have a damaged section of ice and the ice is flowing, it just transports from upstream to downstream. It also can evolve as the ice shears. As crevasses can grow if the ice is pulling itself apart or is shearing, but also crevasses can heal if the ice is pushing itself together. You have a compressive state. So you have this set of equations you can use to describe how the ice evolves and how the damage evolves. And this is work with some more collaborators at the University of Michigan. And this is still fairly new, but what the neat thing is we're looking at these ice tongues in the Amazon Sea region, and we can evolve steady state using this damage stuff. And it turns out that when we do this, we can reproduce the actual shapes of these ice tongues, and you can reproduce where the calving happens. So you can think of calving when an iceberg breaks off as what happens when the cross reaches all the way through, right? When a cross reaches all the way through, the damage gets to one, the ice is no longer part of the upstream ice and it breaks off. So we can predict where the calving front is, which is actually a pretty exciting thing because up until now it's been pretty, it's been sort of much more hand wavy. And if we evolve these things, like we're evolving this ice tongue, we can actually, and we include the calving based on this damage, we can actually evolve some pretty realistic looking ice tongues, which is a pretty neat thing. The other thing is that, and we tried this in the West Antarctica. Basically, we just ran this damage to steady state to basically starting from zero, and then we laid them on top of the actual satellite pictures, and you can tell they agree pretty well. Like the places where purple are places where you have high damage, white is less damage, and you can tell we're matching the patterns we're observing from the satellite pictures pretty well. We're matching the shear margins, we're matching where the crosses are, et cetera. So this is pretty exciting. We can start to predict this and evolve it sort of from in our model in a reasonable way, and then once you guys can predict things like calving events and predict when when you're going to lose your ice shelf, which is actually a nice thing to have. I think I'm going to stop it there and see if there are any questions. So, any questions?
Any questions for Dan? Don't be shy.
Yes.
So why do you guys use a finite volume method? You have three equations, right? One's like a convection equation, one's basically like a Stokes equation, and temperature equation. Like, is there a reason why you guys chose finite volume?
There are a couple of reasons why we chose finite volume. The first is I've got this hammer, right? So a lot of our adaptive mesh refinement methods play very well with finite volume methods because they can fluxes across a corresponding interface. So we tend to do a lot of things in finite volume methods, and a lot of our stuff came out of gas dynamics, for example, which is very conducive to that. Another thing is that conservation is important, and finite volume methods give you that sort of a priori, right? So, and especially in a climate system, they care deeply about, you can't just have water disappear, and so we have that built in by by construction, where the model, other approaches have to sort of make it do fix-ups to make it work. Those are the two main reasons. I mean, part of it is it's what we had lying. It's what we have experience doing, which is probably the most honest answer. And I may justify it later. But any other questions?
Nothing in the Zoom chat.
Right.
Actually, might be one. Is there any time component involved in the system? If so, what time integral method is used?
So we evolve the system. So yes, there's a time component. Right now we're using sort of this hybrid PPM scheme. It's an explicit scheme based on what we do in gas dynamics. So it looks like an advection equation. This has some stability issues, which are unfortunate, and we are working with some people at Lawrence Livermore to come up with better time integration schemes. And also Emma, who's here, is going to help us with is working with us this summer on some time integration ideas too. I don't know if that answers the question or not.
I think it does. Yeah.
All right. I guess I have time for one more thing. The other thing we've looked at is this thing called marine ice sheet instability. Marine ice cliff instability. You may have read about this. This is if you look at the IPCC reports, there's a huge range of possibilities for sea level rise contributions, and part of it is that there's a couple models which have mechanisms which lead to some pretty dramatic loss. And this is one of the major ones. And so these guys, Rob DeCanto and Dave Pollard, wanted to be able to match the paleo record of large sea level rise they'd seen in their model. And they tend to do paleo types of models, so they tend to run fairly coarse resolutions over thousands of years. And what they found was they weren't able to, when they ran these things, and they included things like hydrofracture, with the ice shelves disintegrating. What they wound up with was these gigantic cliffs. So the ice shelf will go away, and you've had this gigantic cliff at the ground where the grounding used to be, and then it would stop. And they looked around and said, well, we don't see cliffs like that in nature, and these cliffs are actually bigger than the yield strength of ice. So they're high enough where if you had a cliff that big in nature, it would crumble. It would collapse because the ice would fail. And so they looked at this and they devised a mechanism where you have hydrofracture. So imagine you have this ice shelf. So, and then you clobber the ice shelf in some, sorry, I can't see it on my screen. You clobber the ice shelf in some way. You wind up with this gigantic cliff, and this cliff fails. And then it leads you to a new mechanism of retreat, known as, like I said, the marine ice cliff instability. And this cliff collapse, and it allows retreat into the Eastern Arctic basin, which previously didn't get retreat, and allows for much greater sea level rise. So it turns out that when they run their model, if you incorporate the original models, it was the lower blue line. This is the sea level rise over time. If you include hydrofracture, you get this green line. But if you include hydrofracture and then cliff collapse, you wind up with this red line. So it's a massively increased contribution to sea level rise. And this got a lot of press. The Washington Post, New York Times, Grist called the ice apocalypse. Even Rolling Stone talked about the Doomsday Glacier. But it turns out the question we had was, is this a symptom of under resolution? Because remember, like we said, if you're not resolved, you're going to get the wrong answer. So this original work was on a 10-kilometer mesh. And meanwhile, we've been doing all these experiments, right, where we've been clobbering Antarctica, and we hadn't seen these persistent cliffs that they were worried about. So what we did is we actually implemented a cliff collapse scheme ourselves, where we could actually keep track of where a cliff was in our model and retreat it in the same way that they did, but do it explicitly and resolve it. And then we ran an experiment where it was designed to trigger this ice cliff instability wherever possible. We took Antarctica, we did once again a range of finest resolutions from 8 kilometers down to 1 kilometer. And the experiment was to run, basically a shelf thinning regime, which thinned the ice shelves and weakened them, and then at some point would make them vulnerable to hydrofracture, and then cap off any floating ice thinner than 500 meters. So basically force the hydrofracture, force what should generate cliffs. And we ran this with and without the ice cliff instability mechanism. And we used the parameters that they use in their parameters in their paper. So if the idea was, if you have a cliff that's 100 meters thick, that was the threshold. That's what triggered the instability. And then if you have instability, then they have a prescribed recession rate. So that would mean that if you have a cliff, it recedes at 3 kilometers a year, based on some observations and some arguments that they made. And then we evolved for 250 years. And results of 8 kilometer, this is the difference of that you get from actually including this mechanism, right? So the red regions are places where you had more ice loss because you had this cliff instability. And particularly, this is matches with what they saw. It's particularly down here in this region, because this is a region that we don't see a lot of responsiveness otherwise. Remember, this is at 8 kilometers. And so if you look at the volume of flotation, the contribution to sea level rise, the top line is just without the cliff instability, and the bottom line is with it. So you see that if at 8 kilometers, we have this massive effect of including this cliff instability. But then we do it at 4 kilometers, and you can see that the response is less. Also, that both responses are more. And we include it, then we go to 2 kilometers. Sorry, wrong way. Or sorry, and then 1 kilometer, and you can see it becomes almost invisible. So the impact of including this cliff instability actually is decreasing over as you improve the resolution, which is suspicious to us at least. And the alternative hypothesis we have is that ice dynamics works to prevent and remove these ice cliffs. So ice doesn't like having a cliff. If you generate a cliff, you're going to get a combination of local acceleration and upstream thinning, which is going to basically bring that cliff down to a manageable size. But these ice dynamics operate on fine scales in the context of these continental models that a 10-kilometer model isn't going to resolve, but we can resolve it because we're using a finer mesh. And this suggests that we need, once again, that we need to resolve these scales to get retreat dynamics correct. So here's an example of Wilkes spaces. This is a cross section through the blue line. The blue is the cross section of the ice. This is the bedrock, and this red is the ice velocity. So this is 8-kilometer resolution. So you can see, or actually, this is the fully resolved one. So you can see that you don't get a cliff, you just get basically things just resolved, but you also have a lot of thinning. If you do it 8 kilometers, you wind up with a big cliff because it gets stuck. So, and that's the kind of thing that would trigger this instability that they're worried about. But like I said, we found out that if we run at a 1-kilometer resolution, we never get the cliffs because, like I said, you have this upstream thinning and this responsive in this fairly narrow region that prevents the cliff from forming in the first place. There's been a bunch of effort in this area in the ice sheet field, and the upshot tends to be that people are taking this perhaps a little less seriously. I mean, a little less worried about it. It's still showing up in projections because you can't ignore it because it's still there in the scientific record, but we're spending more time trying to understand it. And maybe you can see also that the impact isn't zero, right? So even when I do this, there is a slight difference. So it's still a valid thing to happen in some places, but maybe it's not as scary of an impact as people were worrying about. And that really is the end of what I have to say. So, any questions? Any more questions?
So
Yep.
I just wanted to, if I understood it. So basically, the previous group in 2015, they found that because they developed at this low resolution, they developed this cliff instability. Then it made it even made it even worse because those things would crumble and even raise the sea level even higher. But if you did it at a higher resolution, you could find those cliff instabilities. So it wasn't as dire. Am I getting that right?
What it's sort of a little bit reversed, right? So when they ran their model without this, when they ran their model and what they found was they were getting all these gigantic cliffs.
Right.
And they looked around and said, well, first of all, we don't see cliffs, 100-meter cliffs in nature, and people have looked for them. And the other thing is that, there's a lot of theory that says a cliff that high would crumble.
Yeah.
And so it would, you have greater failure. And so what they just said was, look, if we have a cliff that's high, it's going to crumble and we're going to have this instability. What I would argue is that, at some point you have to say, is my model correct? And, if I resolve this more, will this cliff persist? And so when we ran a coarse resolution, we also got the cliffs, and also then which would make sense to have this instability. But when we resolved it better, the cliffs, we no longer have the cliffs because you could have things happen, dynamics happen on a fine enough scale that the coarse model doesn't see them, but they're both on fast time scales and also short distance scales. So that's sort of our statement about that, I guess, or our feeling.
Nothing else in the chat.
Right. Well, I guess it's noon, so thanks for spending an hour with me.
Thank you, Dan.